So it's Pavel Pakhlov, and the title is Recent Experimental Results in B Physics. Please, 30 minutes.
Okay, can you hear me?
Yeah, very well.
Okay, and let me now show you my screen. Just a moment. I will take. Okay, can you see? Can you see the slides?
Yeah, yeah.
Okay, that's nice. Okay, my talk is about the flavor of physics, the recent result in particular in B physics, because I think B mesons are the most interesting part of the flavor part of the standard model. And I would like to say from the very beginning that this year is not very rich of new results in flavor of physics, and this is because the dedicated experiment BEL2 at Super B Factory has just started to take data. They already achieved quite high luminosity, so they beat already the previous record in plus and minus luminosity, which was done at the BEL experiment with KKB accelerator, and they take a lot of new data, but still, of course, a few months of data taken in this year cannot be competitive with the previous 10 years operation of 2B factories. Therefore, new results in B physics, and in the same time, LHCb, which is the main competitor to BEL2, because BEL2 just started and there is no big competition, they also relax still. Therefore, we don't expect many results this year, but I hope very much that in the very nearest future, we will have a lot of new results in B physics. Okay, let me start with motivation for study of B mesons. Let me remind you that standard model is really very successful theory because, of course, it can be proud of many predictions that was confirmed by the experiment. Now all particles predicted by standard model have been observed, and all symmetries, which are basic symmetries of the standard model, are confirmed, and the mechanism of symmetry breaking is established after observation of the Higgs boson, and this confirmed really that the ideas of standard model, which arose 50 years ago, are really confirmed now with experiment. But in the same time, the standard model is certainly not the final theory in physics, and it has a lot of intrinsic problems. It has a lot of some problems with experiment because it cannot explain dark matter, dark energy, and baryogenesis. Therefore, we expect that new physics will appear soon because the problems of the standard model are arise already at the level of 1 TeV scale, which is already close to possibility of experimentalists to test the scale. And flavor of physics is important part of the standard model because it's very rich of some phenomena which are not explained by the standard model because it's a lot of free parameters here, a strange hierarchy of the lepton masses and fermion masses and fermion mixing are not explained, and standard model cannot answer many questions which are very it's obvious to ask why we have only 3 generation, why these certain free parameters are really such as they are, and of course it cannot explain the hierarchy of and smallness structures in the of these parameters. And flavor physics, of course, provides an important part to study new physics at very high energy scale because of loop and box diagrams which are govern some decays of B mesons. And important part of the standard model of the flavor physics is a study of CP violation, because CP violation is really related to box and loop diagrams where the new particles can contribute, and the key importance for testing of new physics beam mesons, where these diagrams are increased. At least they're not suppressed like in charm physics, for example. So the CP violation studies, it's already 40 years history of the ideas of Carter and Sander, who suggested that CP violation in beam mesons should be large and can be measured and can be used for study of the standard model parameters. So they observed that beam mesons, B course, which corresponds to the third generation, should decay to the light quarks via some intermediate states. It requires two W emissions, and in result, the final states with light quarks for B meson and B0 bar are the same. They found that why B and B bar decays result in the same final states, and there is a possibility for BB bar mixing, like in case of kaons. They can generate CPI symmetry, which was estimated by Carter and Sander to be as large as 10%. And now we know that it was too pessimistic estimate, because the CPI symmetry in beam mesons sometimes reach 100%. And of course, CP violation is not only an enigmatic phenomenon that should be studied, but it's also effective tool to search for new physics. And you can see these two plots, which was prepared by CKM Fitter collaboration, showing the possible contribution to BB bar mixing diagram from new physics. You see delta MD corresponding to mass difference between two CP eigenstates in beam mesons is a result of these box diagrams, and it's consists of standard model part and maybe some new contributions from for example, supersymmetry can result in some deviation of this delta MD from the standard model prediction. And this contribution of new physics 20 years ago, can be as large as it can be much larger than the standard model from experimental constraint. But now, after work of two B factories, Babar and Bell, it was constrained to be at least smaller than standard model contribution. But you can see the ratio. So the contribution of new physics can be as large still as 30% of the standard model contribution. So the B physics remains to be very interesting, and new constraints are important to constrain the new physics. And when we're searching for new physics, we should require that the luminosity should be as high as possible, because here there is some citation from sorry, it's in Russian, from the great Russian physicist Lev Okun, who told that 50 years ago he was insisting for continuing an experiment in Dubna with K long, searching for decay of K long to pi plus pi minus. This was before the observation of CP violation by Cronin, Fitch, and company in the United States. And the competitive experiment in Dubna already reached the upper limit corresponding to the effect that was observed 1 year later by American physicists. But unfortunately, this experiment was closed because the director of Dubna that time decided that it's not has no big chance to observe something new, and it was closed just before they probably could observe CP violation. And now we are in a very similar situation. We work with beam mesons that probably can be sensitive to new physics at 1 TeV scale, and we should study as perfectly as possible. And for this, the B factory, super B factory, was built at KK Center in Japan. So the idea was to increase the luminosity by at least a factor of 50 in comparison with the previously uh, achieved by experiment Bell. And the idea how to increase this statistics to increase the luminosity was there was a simple method to increase currents, but it was calculated that to increase currents KK needs a special power station, which will be probably one of the most powerful in Japan. And the better idea was to reduce the size of the beams. So they use the nanobeam scheme for colliding that allowed to increase the luminosity by a factor of 40 in comparison with Bell experiment. And the new Bell detector, which is use the new subsystems. Almost all inner detectors were replaced with new one to cope with higher background level, higher radiation level, and to have better performance. We have much better now the tracking with the new vertex detector with much larger drift chambers and much better system for identification of charged hadrons. And of course, B-physics remains an important part of the scientific program at LHC. So the LHCb detector is a dedicated detector especially designed to study B-mesons, and for CMS and Atlas, the B-physics remains an important part of the scientific program, and we will see this in some examples of the last year. And if we talk about searching for new physics using CP evaluation as a tool to probe the scale of new physics at 1 TeV and higher. One of the most illustrative part how to search for new physics is a study of unitarity of the CKM matrix, which is represented by several unitarity triangles, and this is one of them, which is related to B-meson decays. And we can measure in B-physics, we can measure sides of this triangle, we can measure angles, and if we see some deviations of the triangle from some deviation between the measurements of the angles and sides, or by sides only, or by angles only, we can conclude that there is some contributions which is not controlled by the standard model. For example, the new physics can contribute to the box diagram. In this case, the angles can be different from those expected from the standard model CKM matrix production. And in this case, the sides, which are mostly measured from three diagrams, except for VTD, which is just impossible to measure from three diagrams. All other sides are measured using 3 decays, and angles are measured with almost all of them are mostly measured with box diagrams. Therefore, the contributions which comes only to box and not coming to tree will result in some deviations. So the task is to measure this triangle as much as accurate as possible, and we will see how it's done. So the measurement of angle beta, which is one of the most precisely measured parameter of the standard model, you can see the result from Bell, and you can see comparison between the 3 most accurate experiments, which include Babar, Bell, and LHCb. And LHCb also produced some good results, but still they could not beat the Bell and Babar. And this is actually quite surprising for me, because the statistics at LHCb is quite high, and probably they just need to update this result to have accuracy better than Bell and Babar. I hope this will be in nearest future. And if we talk about the measurement of another angle alpha, it requires much more complicated analysis because of penguin pollution of the measurement, because in addition to the tree diagram b into pi plus pi minus, there is a penguin contribution which can result in the same final state, and the phase from penguin contribution is different, and the ratio of penguin to tree diagram is not known. It cannot be predicted theoretically. This results in some this is results in situation when we measure some angle, but we don't know how it's related to alpha. The idea was suggested by theorists Granau in London. They proposed to use isospin conservation in strong decays and using isospin relation, it's possible to extract alpha almost without model dependence. Of course, there is some systematics from the isospin assumption, but if we measure 6 final states, including pi plus pi minus, pi plus pi 0, and pi 0 pi 0, we can extract alpha without model dependence, and this is really done during 10 years of operation on B factories, and in future LHCb can contribute to measurement on only of the charged final states, improving this accuracy, but BEL2 will contribute to all possible final states, including neutrals, which are important for measure of angle alpha. Therefore, now the accuracy, as you can see, is about 2 or 3 degrees, and in future, in 5 years, it's expected to be smaller than 1 degree. Okay, BEL2 has shown this year the first results using very small data sample in comparison to BEL. You can see this is just 3% of the data that was achieved, that was taken by BEL. But already with this data, the first results are available. So BEL2 measured the parameter sine of 2 beta in CP violation parameter in B integer psyche null KK0. Of course, the accuracy is still much worse because statistics is just taken during a few months. And the first results of reobservation of B into pi plus pi minus and pi plus pi 0. It's also shown at the last iChip conference. And now I will talk about angle gamma, which is measured in the decay of B into dk using the fact that sometimes we can distinguish between D0 and D0 bar. If, for example, D0 decays into CP eigenstate like K plus K minus. In this case, we don't know which 3 diagrams, the first or the second one, contribute to this final state, and the interference, because there is a relative phase, weak phase between them corresponding to gamma, this resulted in CP violation. So we will see, for example, for B plus and B minus, different probabilities of the decay into dk when D0 is not distinguished from D0 bar. The new method was proposed by theoreticians, and it was actually used by Bell before it was suggested by theoreticians, is to use the final state short pi plus pi minus, which has a very high branching fraction, and this is even more interesting results because you can see the relative phase between different parts of the Dalitz plot, which is okay. The Dalitz plot for D0, tact as D0, is shown at this picture. You can see very nice interference pattern here when K star and rho meson interfere, and even K star bar, which from WKB with surprise decays is seen here as a band, horizontal band here. And the accuracy, present accuracy is limited by statistics. You can see that angle gamma is measured already with relatively good accuracy. And if we compare with alpha and beta, it is still the worst measured angle. Therefore, improvement here is very much important. And it was done by LHCb just recently using 3 methods. The first one is to repeat those used at B factories, that is to have B meson into dk with Dalet's analysis of D0 decaying into K-shot by plus per minus. And they measured the angle gamma, which is consistent with the previous result from Bell and Babar. Accuracy, you can see, is 5%. But they also can use another method, is to use the decay of B0 to D plus pi minus. Again, there is a possibility of interference due to BB bar mixing and due to the fact that D meson can be produced from W decays to D plus or from the B part of the B mesons. It means that B0 can decay into D minus pi plus and D plus pi minus with different amplitudes, but it's not so much important. Important thing that the relative phase between these two diagrams is related to gamma, and we need to study indirect CP violation to measure gamma, and you can see the result. There are two regions which are allowed by this study at LHCb, and it's quite typical situation when there is an ambiguity in the results, because here again we have we measure some trigonometrical function from the parameter which we are interested in. And therefore there are some twofold or fourfold ambiguities in the results. Important thing that LHCb is also used the third method. They use B sub s decaying to D sub s k plus or D sub s chi minus. Again, there is a possibility for interference between them because of B sub s mixing. The study is more complicated in comparison with direct CP violation, because you need to study time-dependent CP violation with tagging and with a perfect resolution of vertices. But for HCB, it's possible to do, and they measured angle gamma, which is more than 2 sigma different from B sub s from those measured in B plus and B0. You can see the picture in the right bottom part of the slides. The red one is probability to measure angle gamma in different modes, and there is a more than 2 sigma disagreement between these two measurements, which can be quite intriguing, because this probably can indicate that in B sub s we have some extra phase which appears from the B sub s mixing. But of course, this is just 2 sigma. We need to wait for new data from LHCb, which hopefully appears next years. And if you can see now the situation, the history, the situation with the unitary triangle measurements during the last more than 20 years, we can see that before B factories, the allowed area for the upper apex of the triangle was extremely big. So then in this year, 2B factories started to work, and they improve accuracy. Finally, before the start of L2 and new measurement of LHCb, the situation was quite perfect. We can see that all measurements are consistent, but the consistency is still at the level of 10%, which allow to the contribution of new physics at this level. Therefore, the improvement in accuracy is important. And now I will talk about some new results from 3 LHC experiments, LHCb Atlas and CMS. And first one is a study of CP violation in B sub s decay. B sub s decaying into GPSI 5 is important channel. It's a golden mode for B sub s, because according to standard model, the CP violation in this decay should be perfectly consistent with 0. The prediction of the standard model is less than, I haven't shown this. This is milliradians. So it should be almost zero. And the predictions zero, and the experiment this year it was done at CMS. You can see the huge number of events of B sub S meson candidates at the left plot, and their time evolution fitted with possible CP contribution is shown at the right plot. And the result that if we combined, CMS combined the first data and the last data, this red ellipse corresponds to the allowed area for delta gamma, and B sub S measurement is consistent with zero. And here are the results from other experiments. All of them are consistent with zero.
Pavel, I'm sorry, 5 minutes left.
Okay, okay, I will finish in 5 minutes because I'm already close to conclusion. The new measurement, another interesting channel is B sub S decaying to mu plus mu minus. It's a benchmark final states because in addition to standard model, which is extremely suppressed for this final state, the new physics, for example, supersymmetric particles can increase this final state significantly, because for B mesons, it's suppressed by chirality of muons in the final states, but new physics can just be not left-handed and increases final states significantly. And now Atlas is measured this final states. It's also C, the signal with a high significance. CMS is updated their results, and you can see the table. You can see that for B sub S 2 mu plus mu minus, all three experiments see the signal, and all of them has the measured branching fraction exactly 1 sigma below the standard model expectation. It can be intriguing. Of course, the significance is still very low. For B0, this branching fraction is tiny and is still not seen. You see the upper limits from CMS and Atlas, as well as also consistent with zero result from LHCb. Interesting result from LHCb for lepton flavor violation in BD case. So they improve the upper limits, for example, for the decay of B plus into Ka, mu plus E minus. You can see there is no even background events in their contribution, in their distributions for these final states, and their upper limit is almost 2 orders of magnitude, okay, 1 order of magnitude better than previously achieved by Babar. Interesting results in the that LHCb can reconstruct the final state K plus mu tau. It's difficult because tauonic decays are always with neutrino, but they use the special trick. They use B sub 2 tagging, so they try to reconstruct B plus decaying, which is the product of the B sub 2 decaying to B plus K minus, and they see no signal here, and the upper limit is better than Babar, already moderately improvement compared with Babar, and also B0 and B sub B0 and B sub S0 decaying to mu tau. It was also for B0 done by Babar, and LHCb improved it by a factor of 2, and for the first time measured the upper limit for BS into mu tau. Finally, my last physical slide is the steps for studying of the photon polarization in penguin decays. Again, important contribution, important tasks for LHCb and Super B factories is to measure the photon polarization, because in the standard model, the photon from this decays is always left-handed, but any new physics can change the situation, and right-hand contribution can be also contribute to the final states with photons from B hadrons decays. Important thing, LHCb for the first time observed the radiative decay of lambda B to lambda gamma. It's very nice channel because the photon polarization is difficult to measure. Yeah, you need, for example, to use photon converted into plus and minus, which is very difficult to measure because you need to measure the plane of conversion. But for lambda b to lambda gamma, you don't need to touch photon. You can measure the polarization of photon using lambda, because lambda is fermion and lambda b is fermion, and the photon polarization is correlated with lambda polarization. But lambda polarization can be measured because of p violation in the decay of lambda to proton pi. Therefore, potentially this is a very nice channel to measure the polarization of photon. Unfortunately, now the statistics is too low. It's only 65 events observed by LHCb. But when the statistics will be, say, 100 events, they can really make important measurement of polarization. Another possibility to measure polarization is to study the decay of B sub s to phi gamma. And here you need the time-dependent analysis, because there are three contributions which are related to chirality of photon. S and R delta and C can be used to search for both new physics and measure of polarization of the photon. LHCb made these results and shown last year. You can see the numerical results here, and I would like to say that all of them are consistent with the standard model still. So my summary, there are a few slides of summary. First of all, the present situation with contribution of new physics to box diagrams are shown at the left plot. And already in 5 or 2 years, we improve the upper limit for the new physics and constrain the new physics contributions already at several TV scale by upper diagram. Or alternatively, we observe some new physics if we found that the contributions in the box diagrams are different from zero. I would like to say about Bell 2 experiment, which has just started to operate, just started the data taking. And in 5 or 7 years, the accuracy in measurement of all angles will be improved by a factor of 5 or so. And after that, we can hope that we can observe the new physics by discrepancy in the measurement of the unitarity triangle parameters. And finally, I'd like to show that Bell 2 has already achieved the luminosity higher that okay, it's a factor of 3 higher than previously achieved by Bell, and it's still improving from month to month, from day to day. And in Bell 2, after summer shutdown, will start in few days to take the new data. Okay, thank you very much. That's all what I'd like to say to you.
Thank you very much, Pavel. There are a few questions in chat. Anyway, the first one, why CP violation is seen worse in D mesons? Is it due to CKM matrix?
It's mostly due to G mechanism, because the contributions from box diagrams, from loop diagrams in charm mesons is suppressed by G mechanism. Yeah, because of course in case of B mesons, the contribution of box is cutted by T quark mass, which is much higher. In case of D mesons, it will be cutted by B mesons. It means already by a factor of 20 squared smaller. And also, in case of B mesons, CKM box diagrams are not CKM suppressed.
And another question, which is not appropriate to your talk, but I cannot skip it. Any recent results in glue ball searches? Yeah.
Yes.
Looks like, yeah, the guy just,
there are new results from LHCb. I haven't mentioned this here. It's I'm not sure that they're related to glue balls, but they observed some new resonance in GPSI, which probably means tetraquark. But I think in the question, blue balls means all exotics. Yeah.
Yeah. Okay.
So, but okay, this is not a topic of my.
Yeah. Yeah. Okay. So no more questions. So Pavel, again, thank you very much for your
Thank you very
excellent
much
talk.
for.
Yeah, very informative. And ladies and gentlemen, it was the last report of our first plenary session. So plenary session is over. Thanks, many thanks to everybody in the audience, and good luck with the conference further. Goodbye.